We're going to start this lecture by working on sampling distributions. That's section 7.3. Section 7.3 is on page 319. And this is going to be a very important concept that we're going to learn today. So this concept has to do with how we're going to relate populations and samples. So because that relationship is very important. Later we're going to learn how to obtain information about a population given a sample. So we know now that if you are doing counting, if you are counting things, you have a discrete data set. You can use a probability histogram, or you can use a discrete probability distribution to compute probabilities of events. Also, if you are working with measurements, you know that this is continuous data, and you can use either a probability density curve, or you can actually use the probability distribution if you know a little bit about calculus. Otherwise, you only need to use the curve and a language or language R, or a calculator like the Texas Instrument to find values for probabilities for given events. So the important thing is that these tools are for populations. So for populations, and you can get probability values for individuals from these populations. So for a single element, single item. So in other words, n equals just 1. But what happens when you start selecting more than one person or more than one value from a population? So you start creating samples. So when n is greater than 1, then you have a sample, and you can no longer use the distribution, the discrete or the continuous distribution to compute probabilities when you are working with samples. So now we need to know how these distributions are going to be obtained. So just let's say that you have a population. It can be a discrete probability distribution or continuous probability distribution. It doesn't matter. So you can use any population. It can be this, it can be this one. So the idea is that you're gonna collect samples. So you start collecting samples from each of those. From now on, I'm going to use just the symbol for a population that is following or is consisting of discrete data, but this explanation is valid also for a discrete population. But the problem is that you have a population, and you're going to collect samples, not just one sample, many samples. So you're going to collect a sample with a fixed size. That's important. Let's say n equals 3, then you collect another sample with n equals 3, and you collect another sample with n equals 3, and you start working these samples and finding statistics. So for example, you can find the mean for the first one, you can find the mean for the second one, you can find the mean for the third one, and so on. So you continue collecting samples. So a lot of samples, 4, 5, any number of samples. The greater the number of samples, the better. It's going to be better for you to learn about the distribution that is going to follow these samples. So now the problem is not the distribution that a single individual follows, which are just this distribution that we learned from previous section. No, now the problem is what is the distribution that the means are going to follow as a group of means, as a population of means. So we are creating a new kind of population. This is going to be a population of means, and this population of means should follow a distribution. But what is that distribution is the purpose of this section. So Let me just continue with this kind of idea. So we have another population. So these are our population. This is the population. You can use either of those. So from now on, I'm just going to talk about a population like a continuous population, but the explanation, as I said before, is the same if you have a discrete probability distribution. So let's say that we're going to collect samples again. And now my samples are going to be of size 7. And I'm going to collect a lot of samples of size 7. And so on. But now instead of computing the mean, I'm going to compute the standard deviation. So the standard deviation for each sample. So now I'm going to obtain a population of standard deviations. A population of standard deviations. And this population of standard deviations follows a distribution. What is the distribution? That's what we're going to learn in this chapter. So, and we can do that also with another kind of statistics that you can compute from a sample. So the important thing is that there is a relationship. There is a relationship between the original population and the distribution that your statistic follows. We're going to call these distributions, the distribution of our statistics, we're going to call them a sampling distribution. A sampling distribution. So there is a relationship. So we need to find this relationship between these two kind of distribution, the distribution of the population and the distribution for the samples, the sample statistics. So either the distribution of means, the distribution of the standard deviations, and so on. So there is a theorem that says that if the size of the sample is large enough, then you're going to know the kind of distribution that you're going to follow. So if n is large enough, what is large enough? Greater than 30. Or if the original population is normally distributed, then we can apply a theorem. So the theorem is the Central Limit Theorem. So the sampling distributions follow the Central Limit Theorem, which is described on page 323. So let me show you. So your book is providing some simulations here on this page, where you have the original population, for example. That's the original population. This is a discrete distribution. You can see this is a probability histogram. So we can look at the original probability distribution here on page 322. So this is the probability distribution. Is just for 5 values, 0, 1, 2, 3, 4, and the given probabilities for this. So this is a discrete probability distribution, and we started collecting samples from this distribution. So for example, we collected samples of size 3, a lot of samples, thousands of samples, and we computed the mean for every sample. And then that population of means was plotted, and this is the kind of distribution that population of means for samples with size 3 follow. And then we increased the size of the sample and repeated the experiment. Now the sample size is 10. And with that sample size and a lot of samples, thousands of samples, we created a new population of means, computing means. And this is the distribution that those means follow. So this is the distribution for the means. Now, in the next step, the author of this book decided to collect samples of size 30. So with samples of size 30, the means for every sample was computed, and the collection of samples of the means of those samples were a new population of means, and the corresponding distribution was this. So you can see that once you get the threshold of n equals 30, the distribution that the means follow is a normal distribution. It's a symmetric distribution. So that's the important thing about the central limit theorem. It's telling you the situation in which you can just have a relationship between the original population and the population of means, and it's going to be important, this relationship. So what is that relationship? If x bar is the mean of a large, and this is important, large means n equals greater than 30. So a large simple random sample from a population with mean mu. So the original population has mean mu and standard deviation sigma. Then those means follow a normal distribution, and that normal distribution, this one, is going to have a mean mu for the means. This mu for the means is going to be equal to mu. So in other words, the mean for this distribution is the same as the mean for this distribution. That's the first finding that is important, that is indicated by the central limit theorem. The other important finding is that the standard deviation of this distribution with n greater than 30 is going to be equal to the standard deviation of the original population divided by the square root of n. So now there is a connection between the original population with mean mu and standard deviation sigma and the population of means with size equals 30 or greater, where the mean for this population is going to be the same as the mean of this population, and the standard deviation of this population is going to be equal to the standard deviation of this population divided by the square root of the sample size. So that is going to be the important thing. The other point is that if this original population is already normal, then the size of the sample doesn't matter, but you still need to use the sample size to compute the standard deviation of the new sampling distribution. This is going to be my sampling distribution. This is a population distribution. This is a sampling distribution. It's the distribution, in this case, of the means. Later, we're going to see the distribution of the standard deviations or the distribution of proportions. But now, from now, the only thing that you need to know is that there is a connection between the population and the sampling distribution. As long as you comply, you satisfy the criterion that the simple random sample size is greater than 30, or that the population is normally distributed. So you have here the steps to compute probabilities. Now we can compute probabilities related to samples, not related to individuals as before. So now we can compute probabilities regarding samples. So the first thing is that you need to be sure that the size is greater than 30. So you can use the normal curve. Then you're going to find the mean of the new distribution. The sampling distribution is going to be equal to the mean of the original population. And you need to find the standard deviation of the new distribution, of the sampling distribution. And then you're going to start working the areas as we did before. So we're going to work an example now to apply this new idea of the sampling distributions, which is just the idea of trying to use the information of the sample to to know about the information about the population. That's what we're going to do much later. So let me just have here the central limit theorem. So you have a population and you have the sampling distribution. The sampling distribution, which is just for the population of means of the samples or the standard deviation of the samples and so on. So now the central limit theorem says that if n is greater than 30, then the mean for this one, so the mean of this distribution that we use denote by mu of the means is going to be equal to the mean of this population. And the standard deviation of this distribution of means is going to be just the standard deviation over the square root of n, when you know the standard deviation of the original population. So this is the central limit theorem in a diagram. So let's work on a problem. So we're going to work on example 7.20. So example 7.20 on page 323. So let's look at that problem now. So we need to read carefully now, because now every word is going to be very important. So recent data from the US Census indicates that the mean age of college students is mu equals 25 years, with a standard deviation of sigma equals 9.5 years. Then a simple random sample of 125 students is drawn. What is the probability that the sample mean age of the students is greater than 26 years? So the important thing now is that they are not asking about the probability that one individual age would be greater than 26 years, not just a single individual. They are talking about this, the mean of the sample of those ages is going to be greater than 26 years. So they are talking now about the sample mean. So they are talking about a sample. So we need a sampling distribution to solve this problem. So in other words, what we have now in this problem is first an original population of college students, the student ages. So this is a population of ages of college students. So this population has a mean of 25 years and a standard deviation of 9.5 years. But then they are talking about one sample was collected, one sample with n equals 125 students. So, and we want to know, so if you computed the mean, so we want to know about the mean. So what is the probability that the mean of this sample that we collected randomly is going to be greater than 26 years? So check here, they are talking about the probability that the mean of the sample. They are not talking about the probability that one single student might have 26 years if you get a student randomly selected from this population. That's what we did before. This is for a single student. But now, this is something that we covered in the previous section. So this is section 7.2. Now section 7.3 is that now we are interested not in the probability that a single individual is going to be greater than 26 if you get an individual for the original population. No. Now what we want to know is the probability that the mean of the sample that you collected from here with 125 students, that mean is going to be greater than 26. So we're going to need to use now a probability distribution for the mean. So we need a probability distribution for the means of those samples, the means X bar. So it's going to be now a new probability distribution, and this probability distribution is just a lot of values of means here, a lot of values of means, but this distribution has a mean too. Is the mean of the means. And what is the mean of the means? It's just the same mean as of the population of college student ages. So it's going to be 25 years. Now, what is the standard deviation of this distribution? Is going to be just the standard deviation of the original population divided by n. So this is going to be 9.5 over the square root of 125. So with this new distribution, now you're going to be able to look for the area. So this probability is going to be this area. So this is the probability that the mean is greater than 26. That's the area. Is equal to the area to the right of X bar equals 26. So we're going to use the same formula as before. We have two courses of action. We can find the z-score now. So first, using the z-scores, so we're going to find the z-score for that mean. Is going to be just the mean minus the mu of the means. So the mean of the means over the standard deviation of the means. So it's just 26 minus 25 over 9.5 over the square root of 125. You can do these operations. So 26 minus 25, use parentheses, and you can do this division first. So you're going to get 0.85. So this is going to be 1.18. So now you can find the probability that the mean is greater than 26 is equivalent to the probability that the z-score is greater than 1.18. So you know that when you get areas to the right, you're gonna need to use 1 minus p norm, that's z-score. So this is equal to 1 minus p norm of 1.18. That's the first method. The second method is just let's write here, without using the scores. So directly using just the value. So the probability that the mean is going to be greater than 26 is just 1 minus p norm, and we're going to provide that mean. We're going to provide the mean of the means and the standard deviation of the means. So this is equal to 1 minus p norm. The mean that we are interested in is 26. The mean of the mean is 25. And The standard deviation of the sampling distribution is 9.5 over the square root of n, which is 125. So this is the second way to get the answer. So let's use R to find the solutions for this problem. And then one more problem, and then you're going to have a chance to play with these sampling distributions. So let's start with the first case. We only need 1 minus p norm of 1.18. So that is going to be 0.11931. Now that's with the first method. With the second method, we only needed to enter the values directly without computing the z-score. So 26,25, the mean of the means, and then 9.5 over the square root of 125 students in the sample, and you get the same or very similar answer, because in the first case we rounded the z-score. We rounded off the z-score. So the probability that the mean of that sample with 125 students is going to be greater than 26 is just 0.11. So that's the solution for this problem. So we're going to solve one more problem, and then you're going to have the opportunity to work on 3 problems from the corresponding section. So now we're going to solve a problem, example 7.21. So let's see. So this is example 7.21 on page 324. So let's read the problem. The problem is here. The problem is about a certain brand of cattle, which is the most popular breeds of beef cattle. And based on data from the corresponding society, the mean weight of 1-year-old Hereford bull is 1135 pounds with a standard deviation of 97 pounds. So that's the population of bulls, of bull weights. And would it be unusual for the mean weight of 100 head of cattle to be less than 1100 pounds? So we're going to work this problem now. This is about not an individual bull. It's about a group of 100 bulls in our sample. So let's work on this problem now. So we need to write the information from the population first. So we have a population. This is a population of the corresponding animal weights. And they say that the mean of those weights is 1135 pounds, and the standard deviation is 97 pounds. And then we collected one sample with size n equals 100. And as in the previous problem, we have more than 30 individuals in our sample, so we can use the Central Limit Theorem. So in this case, again, we are interested in the mean of that sample. We want to know the probability that the sample is going to be less than the 1100 pounds. So we want to know the probability that the mean is less than 1100 pounds. And not just that, we want to be whether this value is unusual. So what we want to know is to know whether this probability is less than 0.05, as we know that this is the threshold for unusual events. So we're going to find the probability that x, the mean of x, is less than 1100. So again, the size is greater than 30, so we can apply the central limit theorem. So that means that we can use probability distribution, a normal distribution for the means. So this is the sampling distribution for the means, for all means, for a lot of samples. So it's a normal distribution. And we know that the mean of those means is going to be equal to the original mean of the original population, so 1135 pounds. The standard deviation is going to be just the standard deviation over the square root of n, so it's going to be 97 over the square root of 100, so it's just 9.7. So those are the parameters for the sampling distribution. Now we want to know the probability that you have here a value, a mean of 1100, and we want to know this area. This area is going to be the probability that the mean is less than 100. So again, we have two courses of action. The first one is using the z-score, and this is for the students that you already know how to use z-scores, using the z-score. So we need to find the z-score. Then the z-score for the mean is going to be just the mean minus the mean of the means over the standard deviation of the means. So this is just 1100 minus 1135 over 9.7, which is the standard deviation for the sampling distribution. So we do this computation and we find negative 3.61. That is the z-score. Now we know that the probability of x less than 1100 is going to be equal to the probability that the z-score for that x bar is less than negative 3.61, and that is going to be just p norm, because this is the area to the left, p norm of that z-score. So it's going to be p norm of negative 3.61. So we're going to find this value using R, but first I'm going to write the other method without using z-scores. So we're going to go directly. The probability that the mean is less than 1100 is just p norm. We're going to use the mean of interest, the mean of the population of means, the standard deviation of the population of means. So this is just p norm of 1100, 1135, and 9.7. So this is what we're going to do now with R. So let's do these computations by using our language. So we have first p norm of negative 3.61, and we get a very, very low value. It's just 0.00153985. Now this is when you use the z-score, when you use directly the given values. Then you type 1100, 1135 for the mean of the means, and 9.7 for the standard deviation of the means. So we get a very similar value, 0.0001541,362. So now we need to answer the question, is this probability value less than 0.05? So yeah, you can see that this value, so the probability that the mean is less than 1100, the bull weight is less than 1100 pounds, is less than 0.05. So that means that a bull weight of 1100 pounds or less is unusual. So that's the answer for this problem. So now you're going to have your first round of exercises for the assignment corresponding to this class, this lecture, the class work. So they are going to be from section 7.3, exercise set, on page 325. So you're going to work problems, 3 problems only, 10, 12, and 14. So now remember you are working probability of events involving samples. So let's see, page 325 is here, 10, 12, and 14. So you have here the 3 problems. Okay, 10. You have here a sample of size 126. So you have the sample size, you have the mean and the standard deviation. And then you're going to solve those problems. Problem 10. Remember, when you are finding percentiles, is when you are giving the area, 0.55, the area to the left, and you're going to use Q norm. So that's similar to a problem that we solved for the last class. So you have problem 12 here and problem 14 here. Now we're going to cover section 7.4 about the central limit theorem for proportions. So first we're going to have the definition of a proportion in your book on page 328. So in a simple random sample of n individuals, let x be the number in the sample who have the characteristic. So for example, remember successes, failures, something that we learned from previous chapters. So the sample proportion is p hat is going to be x, the number of successes, over the number of trials. That's one way to see the proportion, the sample proportion. Or simply is just x is the number of people that satisfy a condition over the total number of people in the sample. So that is going to be the definition of a proportion. Then the central limit theorem, to be applicable, to be able to apply the normal distribution for proportions to do computations of probability, there are 2 conditions that need to be satisfied. The first one is that the size of the sample times the proportion of the population is going to be greater or equal to 10, and also the product of n times 1 minus p is going to be greater or equal to 10. If that is satisfied, if those conditions are satisfied, then we can use the normal distribution as our sampling distribution for proportions. That normal distribution is going to have the following parameters. So the mean for those proportions is going to be equal to the proportion of the population, and the standard deviation for those proportions is going to be the square root of p times 1 minus p over n. So we're going to solve some problems to understand how to apply the normal distribution in the case of computing probability related to proportions. So we have then our section, the central limit theorem for proportions. We have the definition of a proportion. Again, it's just x over n. And also, when you have a population and want to determine the proportion, then you divide x, the number of people satisfying a condition, over the total size of the population. So remember, x is just the number of individuals that satisfy a given condition. So it's like a success. Then the way that we derive the sampling distribution proportion is the same way that we did for means. So we have a population with a proportion, a parameter p, and we are collecting a lot of samples with the same size n, and we compute for every sample the corresponding proportion of that sample. So we're going to have a collection of values p hat, because they are for samples, and then there is going to be a population of sample proportions p hat. So the central limit theorem says that if you satisfy these two conditions, this is equivalent to the other condition that we have n greater than 30 when we were working with population of means. Now we're working with population of proportions, so the conditions are slightly different. So np greater than 10 and n times 1 minus p greater than 10. So you can use, according to this central limit theorem, once you satisfy these conditions, you can use the normal distribution to compute probabilities related to that sample proportion p hat. So the only thing that you're going to have now is that the mean for this normal distribution is going to be equal to p, the proportion of the population, and the standard deviation for this normal distribution is going to be the square root of these quantities, p times 1 minus p over n. So we're going to solve two examples, and then you're going to have the chance to work on this. So we're going to start with example 7.23 on page 331. So let's read the problem, and then we're going to proceed to solve the problem. So 7.3 is here on page 331. So it says that according to Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. So anytime that you see this kind of parameters of population in terms of percentages, is because they are talking about proportions. So 27% of Americans like ice cream with a chocolate flavor. So 27%. So if a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.30? So that's the problem. So we're gonna need to write the values. So we have a population of people in America. This is the population of Americans. This is just Americans, and only the proportion that population of Americans, the proportion that like the chocolate flavor is 27%, so it's going to be 0.27. So that's the proportion for this population of Americans. Survey about ice cream flavors. So then we collect a sample. So a sample with size equals 100. And we want to know the probability that the proportion for this sample is going to be greater than 0.30. So that's what we want to know, the proportion. So this is capital P, and this is lowercase p. The proportion greater than 0.30, we want to know the probability. So this is probability, capital P, and this is proportion of a sample. So we're going to use a distribution that can be used as long as we satisfy the central limit theorem conditions. So conditions, let's check the conditions. So we have NP should be greater than 10. So we have N 100 and P is 0.27. So this is going to be equal to 27 and is greater than 10. The condition is satisfied. Then the other condition is N times 1 minus P should be greater than 10. So we have 100, then we have 1 minus P is 0.73. So this is going to be equal to 73, and that's greater than 10. So those conditions are satisfied. That means that we can use the normal distribution to find that probability that we are looking for. So the normal distribution that we're going to use is the one that is going to have here mu for proportions is going to be equal to P. So in this case, it's going to be equal to 0.27. So this value is 27. 0.30 is going to be around here. So this is what we want to know, this area. So the standard deviation for this distribution of proportions is just the square root of P times 1 minus P over N. So this is going to be the square root of 0.27 times 0.73 over 100. So if you do this operation, you're going to find that the standard deviation for this normal distribution that we're going to use to compute probabilities related to proportion is going to be 0.044396. So those are the parameters for the sampling distribution. So this is the sampling distribution. These are the parameters. These are the parameters for the sampling distribution that we're going to use now. So we have two ways to do that. Remember, either computing z-scores using z-scores or not using z-scores. So first, using z-scores. So we're going to need the z-score for the p-hat that we want to know about. Is going to be just p-hat minus the mean of the p-hats over the standard deviation of those p-hats. So it's going to be 0.30 minus 0.27 over 0.044396. We do this operation by using our calculator. Don't forget this parenthesis to prevent mistakes. So we're going to get 0.68. So now the probability that P hat is going to be greater than 0.30. So again, you have a z value here of 0.68. We want this area. This is the area that we are looking for. This is equivalent to the probability that the z-score for that p-hat is greater than 0.30. 68, and this is equal to 1 minus, because the area is to the right, 1 minus P norm, because we can use the normal distribution because of the central limit theorem. So this is 1 minus P norm of 0.68. So that's the first way to work this. The second way is without using z scores. So without using z scores, the probability that p hat is greater than 0.30 is going to be just 1 minus P norm, because this is greater than, so it's an area to the right. So 1 minus P norm, and we're going to give P hat, the mean of the P hats, so the P hat distribution, and the standard deviation of P hat. So this is equal to 1 minus P norm of 0.30, 0.27, 0.044396. So we have two computations to do now, and that is going to be the first problem that we solve by using the normal distribution or the standard normal distribution, depending on the method that you prefer. So in the first case, we're using the standard normal distribution. 1 minus P norm of 0.68 is just 0.24. We're going to write 0.2482, 522. So that's the probability. But we can also use the normal distribution directly. So it's going to be 1 minus P norm of 0.30, 0.27, 0.044396, and we should get a similar value. So we get 0.249604. So the probabilities are close. So it's just the rounding off that makes a little difference. So we have here the solution by using both methods. So now we're going to solve one more problem, and then you're going to have to work on one more problem for the assignment. So we're going to solve example 7.24. Example 7.24 on page 331. So let's see. So we have here that problem. So we're going to use the central limit theorem to determine whether a given value of p hat is unusual. So again, we need to find the probability and compare the probability to 0.05, which is the threshold to classify an event as unusual. So approximately 60% of eligible voters voted in 2016 US presidential election. If a sample of 88 eligible voters were polled, would it be unusual if less than half of them had voted? So let's work on this problem. So first, the conditions. We can just check that the conditions are satisfied here by checking MP is just 88, the sample size, times the proportion, which is 0.6 because it's 60%. So, and that product is 52.8, is greater than 10. The other condition is just 88 now multiplying 0.4, and it's 35.2. So those conditions are satisfied. So now we can just proceed and use the normal distribution as the sampling distribution for proportion. So let's write that down. So we know that NP equals 88 times 0.6 is 52.8 is greater than 10, so perfect. Then N times 1 minus B is 88 times 0.4, and this is 35.2, which is also greater than 10, so we can use the normal distribution. The normal distribution is going to be the sampling distribution for proportion. Sampling distribution for p hat. So we know that there is a population of voters, population of voters, and the proportion of the population that voted in the last presidential election is 0.6, and we collected a sample with size equals 88, and we want to know if it's unusual that half of the population voted. So we want to know if we have here 0.5. So we want to know the probability that the proportion is less than 0.5. So first we're going to need the parameters for this distribution. So mu for the proportion is just p. So mu for the proportion is going to be 0.6. And the standard deviation for the distribution is going to be just the square root of p times 1 minus p over n. So this is going to be equal to 0.6 times 0.4 over 88. So doing these operations, you're going to get a standard deviation for this distribution, 0.052223. So now we want to work on the probability that p hat is less than 0.5. So that's the purpose of this problem. So the first method, using these scores, we're going to need to find the z for this proportion, the proportion of interest. So it's going to be p hat minus mu for p hat over the standard deviation for p hat. So this is just 0.5 minus 0.6 over 0.05 223. So we do these operations, and we're going to find that the z-score is going to be equal to negative 1.91. So finally, the probability that p hat is less than 0.5 is equal to the probability that the z-score for p hat is less than negative 1.91. So this is just on the left, this area on the left, so it's directly p norm of z of p hat. So this is p norm of negative 1.91. So we're going to get a value of probability for this case. Now, without using these scores, so how things change is we're gonna see now. So without using the score. So working directly with the data. So we're gonna have, let's see, just the probability that p hat is less than 0.5 is gonna be just p norm. We're gonna use p hat, the mean for p hats, the standard deviation for p hats. So this is p norm of 0.5, 0.6, and 0.052223. So we're going to use R to determine these two probabilities. And with that, we're going to finish this section. You're going to have one more problem for your assignment. So let's see, P norm of negative 1.91. So this is 0.028, 0.6661. Now, if you don't want to compute the z-score and go directly with the information that is given, then you enter the proportion of interest, then the mean of the proportions, and the standard deviation of the distribution of proportion, the sampling distribution. So you're gonna get a similar value. So 0.02775485. So those are the results. You can see as a slight discrepancy because of the rounding errors when you computed the corresponding z-scores. So that's that problem. So now we're gonna work on the corresponding exercise set. So this is section 7.4 exercise set on page 332. You're gonna solve just one problem. You're gonna solve problem 16 for this section. With that, we're gonna finish this section. So problem 16 is here. It's about smartphones. So let me increase the size. So you have a Pew Research report indicating that 73% of teenagers aged 13 through 17 own smartphones, and then a random sample of 150 teenagers is drawn, and you're going to find the mean, then the standard deviation, then you're going to compute the probability that more than 70% of the sample teenagers own a smartphone, then you're going to compute another probability that the proportion of teenagers owning a smartphone is between 0.76 and 0.80. Then another probability. So 4 probability computations that you're going to work is just more of the same that you already know from previous chapters. The last section that we're going to cover for this lecture is section 7.6, and which is going to be also the last section corresponding to chapter 7, and it's about assessing normality. So this is on page 341. So what is this important? So we have been using the normal distribution as a sampling distribution when we want to know about the probabilities of events involving samples. So, and we know that the Central Limit Theorem gives us some rules, some lines to follow in case that we don't know whether the original population is normally distributed. And one of the main rules is that the size of the sample should be greater than 30. But sometimes we have small samples and we still want to know whether we can apply the normal distribution for the sampling distributions that we might need. So The reason, especially then, to assess normality is when you have a small sample. So this is written here, assessing normality is more important for small samples than for large samples. So there are some guidelines here. So if you see one of these three conditions showing up or being satisfied, then you cannot use the normal distribution. So one of the conditions that is going to prevent you from using the normal distribution is if the sample contains an outlier. You know now how to know whether there is an outlier. There's something that we cover in chapter 3. So check again how to find out whether you have an outlier in your sample. Also, if the sample exhibits a large degree of skewness, so in other words, that the distribution is not symmetric, so you might have one tail larger than the other, that's skewness. Or if the sample is multimodal, so in other words, it has more than one distinct mode. So if you find one of these conditions, then your sampling, your distribution cannot be normal, so you cannot use the normal distribution. So there are many ways to determine normality, to assess normality. This book shows you a lot of them, dot plots, box plots, and many others. So we're going to use just two kinds of the ways to know whether we can use the normal distribution or not. So one is going to be histograms, which are on page 343. So in this case, when you have histograms, what you want to look for is for symmetry. So look for symmetry. And you're going to use just a simple command in R. Remember, histogram, hist of x, as long as you enter the data. So your data enters as a sequence of values. You know x equals lowercase c, and you enumerate all your values. So one is histograms, the other one is going to be normal quantile plots. They are described on page 346. So what you're going to look here in this kind of plot is you're going to look for a linear pattern. So I'm going to use in R two commands. The first is Qq norm of x, or and Qq line of x. So, and in that way, you're gonna have these tools for you to decide whether your sample follows or is normally distributed. So we're gonna start solving just a couple. We're gonna solve three problems. Then you're gonna have one more or two more for assignment. So the first problem is example 7.33 on page 344. So this problem on page 344 is here. So we're going to use a histogram to assess normality. So you can see here the data set diameters were measured in millimeters for a simple random sample of 20 grade A eggs for a certain farm. The results were, and then you have all these values. So we're going to construct a histogram for this data, and then we're going to decide whether the sample is approximately and normally distributed. So you can see here the histogram that was created using this data set for the author, by the author of the book. But now we're going to use our language R to do the same thing. So we might get a slightly different histogram. The important thing is that we are looking for symmetry. So let's work on this. So I'm going to enter the values for the diameters. So let's see. So I am entering here the values in different rows. So first I wrote diameters equals lowercase c, parentheses, and then I move to the next line. In that way, I'm going to be able to check whether I'm entering the values correct. And then when I finish the first line in the data set that is in the book, I press enter to get the second line. And when I finish, then I enter a parenthesis. So now I have my data set there. But let's check the histogram of diameters to see whether we get a similar histogram than the one that is in the book. So that's the histogram. It looks like there is a maximum value near the center, and then this is the kind that you can say this is approximately normally distributed. It's not exact. An exact normal distribution is an approximate normal distribution. So this is just what you're gonna do when you use a histogram to determine normality. So let's check now the next example. So the next example that we're gonna work on is example 7.34 on page 344. So another histogram is going to be constructed. So now is this problem. So we have a shoe manufacturer is testing a new type of leather sole. It's important sample of 22 people wore shoes with the new sole for a period of 4 months. The amount of wear on the right shoe was measured for each person. The results in thousandths of an inch wear. And then we have another data set that we're going to enter into R, and then we're going to look for symmetry in the corresponding histogram. So again, we go back to R, and now we're going to enter the values for those shoes. Okay, so we're gonna use now X11 just in case you want to compare the two histograms, and in that way you're gonna say whether one is more normally distributed than the other. So I'm going to get the histogram for these shoe measurements. So let's check. We'll go to Windows. We get this histogram. Now you can see that there is no symmetry. So you can compare. With the other histogram that we just obtained before. So you can see now that in the first case there is more symmetry than in the second case. So you can treat example 7.33 as a normally distributed sample, and on the other hand, example 7.34, you can say that is a sample that is not normally distributed, so you cannot apply the central limit theorem. So if you have questions about proportions, means, or standard deviation of the sample, you just say, no, I cannot say anything. It's not possible. The sample is not normally distributed. So let's work one more example now. We're going to use now the other method. So now the next example that we're going to work on is example 7.36. So that's the next example. Example 7.36 on page 347. So that's another example. Let's check the problem. So now we're going to use normal quantile plots. So this problem is on page 347. So problem 7.36 is here. So now we have another data set. So a placement exam is given to each entering freshman at a large university. A simple random sample of 20 exam scores drawn with the following results. So we have another data set. Now we're going to construct a normal probability plot. So we're going to use what is a normal quantile plot, and we're going to decide whether that's a normal distribution or not. That's the sample. So we're going to see now the results here. So I'm going to use my R console again. So now I'm going to enter the information for the new problem. Those are the scores. So we're gonna enter the scores in the same way that I did before. So in several lines to be able to see that I'm entering the right scores. And then I'm going to use Qq norm. That's the function with the variable with the data, in this case scores. So I totally forgot using X11, so I just lost the previous histogram. And then I'm going to use QQ line. If you use QQ norm only, what you're gonna see is just this kind of plot. So you can see here that it's very hard to see that this is a linear pattern. This is more like a curve, like a parabolic behavior. But to be sure, you use the second command, QQ line. Is going to give you the best line that fits the data, and then you can just say, if you have the points scattered randomly and evenly around the line, then you can say that the data is normally distributed. Otherwise, you're going to say that it's not. So now you can see here, you can see the line, and these values are not scattered evenly and randomly around this line. So the mirror values are on one side of the region that results from dividing the plane by the line, and the other values, the extreme or the values, the lower values and the higher values are on the other side. So you can see here that this is not a data set that is following a linear pattern. So those are the tools that we're gonna use when we need to check normality. So finally, I'm going to give you the assignment corresponding to this section, and with that, we're gonna finish this chapter. So we have here that you're gonna need to look at section 7.6, the exercise set on page 350. So let me see what are the problems. The problems that you're gonna solve are problems 26. You're gonna build a histogram for that problem, and 28. You're gonna build a normal quantile plot. So these are the two problems. Those problems are based on data sets that are given in a different number. So the data sets are, for this problem, is the data set is in problem 22, and the data set corresponding, you need to check problem 24. So the data sets for these two problems are these other numbers. So you're gonna solve 26 and 28, but you need to use the data set that are given in 22 and 24. So first, I'm going to give you the data sets then. So you have here problem 22. So that's the data set. So a manufacturer of aluminum cans measure the level of impurities in 24 cans, and then you have the amounts of impurities in percent. So that's the data set that is going to be used to solve problem 26. So 26 is here. You're going to construct a histogram for data in exercise 22, and then you're going to see whether the sample comes from a distribution, a population that is approximately normal. So that's problem 26. Then you're going to need the data sets in problem 24 to solve problem 28. So the data set is here. It's a fish hatchery, raises trout to stock streams and lakes. And you get the weights in ounces, and those are the values. So you only need the data sets. You don't do anything else. So you go and work problem 28 with the data set. So you're going to construct a normal quantile plot for the data in exercise 24. And then the same question, you're going to decide whether that sample is coming from a normally distributed population. And that's all for chapter 7. So for this lecture, you're going to compile all your screenshots and use your corresponding app to convert them into a PDF file. Then you upload the PDF file by pressing the submit button in the corresponding classwork assignment on Canvas.